Perfect. Thanks everyone for joining. So a quick overview on the agenda, discussion topics. We're going to first go through test method comparison between single degree of freedom testing and multi-degree of freedom testing. Then we'll talk about system design, how to control all of the degrees of freedom. Talk a little bit about the cube and tensor test systems, which are both multi-degree of freedom systems offered by TENSOR Corporation. And then a brief discussion on methods of control for these various solutions. To answer the question is mostly the goal today of why do we want to go into multi-degree of freedom testing? Replicating real world excitations that you see in the real world is important to replicate that in the lab. Mainly because I potentially could identify new failure modes to products. It's a more accurate representation of what's actually being seen out in the field, and it provides more fidelity for your testing, leads to better product design. Ultimately, it can result in cost savings, weight reduction for your products, and so on and so forth. So the simplest form of vibration testing could be defined as a single degree of freedom. It's been around 70 years or so. Most test labs will only run single degree of freedom, and multi-degree of freedom is becoming more and more common, whether that's 2 degrees of freedom, 3-DOF, all the way up to the 6 degrees of freedom. The reason, more realistic field representation. It's what your products are actually seeing out in the field. It could lead to accelerated testing while maintaining the fidelity of your tests. But really, we want to talk about multi-degree of freedom testing simultaneously leads to additional failure modes not captured in the one DOF world. So the first thing I want to talk about is comparing these using a brief video our sister company, Lansmont Corporation, made. And so they performed a simple test where they rented a U-Haul van, I believe, or Penske truck or something like that. And they put one of their Saver field data recorders out in the back. So this has there's a little green box on the bottom left of the screen there with a bunch of blue cables going into it. That's a three-axis accelerometer. So that's collecting field data, and there's another accelerometer to the right of that by about 24 inches or so. And then just to the north of there, on the other side of that second water jug, is a third tri-axis accelerometer. And the reason we're doing that is we're defining a plane and helping get a better or capture better data on what's happening across that entire surface, as opposed to a single point of contact by one tri-axis accelerometer, or even various single axis accelerometers. Now you'll notice there's 2 GoPro video cameras, one of them producing a wider angle showing all of the water jugs and how everything in the back of the truck is behaving, and a close-up view of this third water jug from left to right over here. So this is just a general test setup for collecting field data. And what you're going to see in this video, we're actually replicating this in the lab. So this video is another GoPro from the bottom of a truck. We actually modified this camera view using these 2 white points down here to simulate the plane that the road is on. So the video in the background is your drive input signal. This is what the input from the road into the truck that you want to replicate in the lab. The reason we did that is so the video you're seeing is from the perspective of the road and not bouncing around with relation to the axis of the truck. So that was some nifty video editing there. The only thing that this doesn't take into account is the tires and motion of the tires. So here you can see the input from the road is bouncing around, and replicating this water jug on the same test setup in the lab on a 6-degree of freedom system, this is the cube 6-degree of freedom system here, we're actually constraining out the pitch, roll, yaw, and 2 horizontal axes in order to provide pure vertical motion. And so this video on the top right is a close-up view of that water container showing the response that this payload has versus the real response in the back of the truck over on the left-hand side. So we'll let this play and watch the behavior of the water, which is what the test object is seeing in the field versus what a 1-degree of freedom shaker system would be replicating in the lab. And it's doing a good job with vertical. There is some slight motion in the horizontal, but it's not a perfect representation of what's actually going on. So now we're going to go into multi-input channels from the test controller to replicate more precisely what's actually going on in the field. So again, we'll just let this play out a little bit. And there is the 2 water jugs again. The one on the left-hand side is the response of the payload in the vehicle, and the one on the right-hand side is the response in the lab. And you can see it's a much better representation of what's actually going on. It is important to note when you're watching this video on the bottom right of the cube top surface, the primary mode is in the vertical axis, and there is some pitch and roll if you watch closely. But if you really pay attention, or zoom, if we did put a camera much closer to that, you could see that it is kind of bouncing around in all of the degrees of freedom. So that brings up the multi-axis system design. So now we can see that the representation in the field can be quite different from what you're seeing in the lab. From team's perspective, it's much better representation to replicate things in the 6-degree of freedom realm. But doing this presents a bunch of different challenges in test setup as well as the design of the test system. So multiple axes require multiple moving parts and interconnection of all of those. So the behavior of how everything connects together and moves while running these profiles is very important. Instead of one actuator moving in a 1-degree of freedom, you have a minimum of 6 actuators that are all moving simultaneously together to produce the response that's desired. Doing that presents a lot of solutions from the kinematics standpoint. One of the typical test setups for 6-degree of freedom systems is a 3-2-1, where you have 3 actuators in the vertical orientation, 2 in one of the horizontal directions, and a single actuator in the second horizontal direction. The reason for doing this is it's more or less the cheaper solution to provide the minimum amount of constraint for all of the motions. And it gives you the full capability of what all 6 degrees of freedom. By actuating the exciters in phase or out of phase, you can reproduce all of those motions with minimal actuators. One of the more important parts of how these connect together are the joints in which allow the rotations to happen. One of the low-cost options is to use swivel ends. They're cheap and they're good for some things. There's an example on the bottom right of this slide where you can see 2 greased swivel ends. And the point of this cross member here is to prevent rotations in the yaw and one of the horizontal axes of that test system. We'll show a video of that a little bit later on. One of the problems for those is they create backlash in the overall product, and it really limits the frequency response of the test system. So by doing that, it's limited to 50, 100, maybe a couple hundred hertz, depending on the application, the size of the table, and payload that you're putting on there. A better solution is using hydrostatic couplings. So whether that, basically it's replacing these greased swivel ends here. The hydrostatic couplings offer high transmissibility, which means the forces and stresses that go through from the test object into the actuator is transmitted 100%. There is no backlash that happens, and you can realize a much higher frequency response. Now they do add a little bit of, a little bit more design criteria in there. The team Hydroball is shown here on a 321 system design. And this Hydroball is mounted on either end of the actuator, which is a good way to separate the centers of rotation and achieve higher angular motion. But by doing that, it puts the actuator in sort of a bending mode. And when you're doing higher frequency testing, it could cause issues with the fidelity of the test, as well as issues with the actuator over time, and in the thin neck of the Hydroball here, it presents higher frequency issues once you get above 250, 300 hertz. So we'll see these in action in a 3 degree of freedom system. We'll have to keep playing this on a loop. But this system over here has 3 actuators down on the bottom in the vertical orientation, all with the Hydroball, so hydrostatic couplings on the top and bottom of the actuator, and a large table that's about 40 inches by 80 inches long, designed to do double pallet loads here. So you can see if you operated 3 actuators in phase, you could get the vertical motion, and then operating them out of phase, you can get the pitch and roll motions as well. As I mentioned earlier, these 3 cross beams provide the constraint for your yaw motion, as well as the X and Y dimensions as well. So by doing that, we're able to run a random profile out to over 200 hertz. I think it was closer to 250, 300 hertz on a double stacked pallet load. The benefits of this design is, again, the higher frequency response on quite a large table, as well as having the friction-free joints to provide higher fidelity test between the actuator and table interfaces. So now we're going to talk about the cube test system for a little bit. The cube is an integrated 6 degree of freedom system. So it has 6 double-ended actuators. There's a picture on the top right shows the stack up with all 6 of those actuators. The aluminum bronze looking component is the team pad bearing. And the pad bearing is essentially a spherical coupling that provides friction-free motion in the translational axes, as well as in the all rotations for which it's connected to. By doing this, the cube box, so the yellow component on the bottom right picture, is not mechanically connected to any of the actuators. The added benefit here is you do not have excess moving weight in different axes when you're trying to excite that payload. So by doing that, if you're moving this in the cube box in the vertical orientation here, you are actually not adding any weird mechanical connection around the horizontal axes, or actuators rather, while you're exciting it in the vertical orientation. And the benefit of that is you reduce moving weight, and you keep everything symmetrical, nice and happy, and you're able to realize over a 500 hertz frequency response. This has an integrated voice coil servo valve down in the center section of the actuator. So in the bottom left, you see a closer picture of that cube actuator, or one of them. So there's 6 of these. And this is actually a dual stage pilot and slave valve with up to 140 liters per minute. So you could still achieve about 40 to 50 inches per second on a cube, all while in quite a compact space. By having all of these actuators so closely together, it reduces the oil column resonance and allows the system to get that 500 hertz frequency band, which is more or less perfect for the automotive industry and a lot of lower frequency, harsher tests than that you'd see for mill standard. It can run 810G and other profiles similar to that. Again, all of the hydrostatic fixtures allow extremely good transmission of forces between the actuator and payloads, which means there's going to be virtually no backlash, as well as no wear and tear on any of the moving parts. So we'll see a cube in action here. So here's another quick video of a cube with a double stack payload showing a multi-axis test. Unfortunately, I do not have the single axis version of this test, but you can see how this payload has one pallet load on the bottom and another pallet load on the top. And you can see once you start adding payloads together, the farther away from the input drive you get, the more play you could see in your payloads. So it's important to consider, adding on a more realistic representation. So again, specific to the package industry, most containers or most trucks, when they're shipping products, will put either one pallet on the bottom or add a second pallet on top. By doing that, the one on top, as you can see here, is seeing much more displacement. We didn't have any accelerometers to measure what the displacement accelerations are up at the top, but you can visually see that it's quite strenuous up there. One more time. Now we'll talk about the Tensor test system. So the Tensor test system, again, uses the integrated pad bearing design on the ends of an electrodynamic shaker armature. Team designed and manufactured this entire thing. The ED shakers are oil guided and oil cooled, and provide a high surface constraint to the table, which allows more captive control over the table. By doing this with 12 different shakers connected to the table, we can use those shakers to control the table mode shapes and increase control out to 2,000 hertz. And that's pretty neat for a multi-axis shaker system. Again, it uses sort of the same technology as the cube, with the ED shakers in there. We pulled it's essentially the cube with the pad bearing assemblies pulled onto the outside of the table structure to reduce that moving weight and provide a smaller area to allow higher frequency response. So this is sort of a premier system for enhanced multi-axis control. Provides more control over the test and over the what the payload is seeing. And so the last thing that we wanted to touch on today was potential control possibilities. So the over-constrained design of the tensor relies heavily on the test controller for providing the control, both from the input as well as measuring and responding to that input and driving, modifying the control parameters to drive the system, especially through the 2 kilohertz bandwidth. So as I had mentioned before, it presents the ability to control mode shapes in the table by using the matrix test controller. So this picture here on the right-hand side of the screen shows typical 6 degree of freedom control for the 3 main axes, so the x-axis, y, and z. And as you can see over this flat random all the way out to 2 kilohertz, there's some mode shapes that start showing up around 1500 hertz and then shortly before the 2 kilohertz. And you can see that in the X, the Y, and the Z. And the Z is perhaps the worst with this sharper resonance just before 1 kilohertz, I believe. The 7-DOF control is essentially using the matrix to define a virtual control channel that is above the tensor table. So it's not a real point of control. You're using accelerometers to kind of define that out in space and then controlling based off of that. And that was just gathered based off of the mode shapes of the table. And you can see once you add that 7th degree of freedom control into the control parameters, you basically clean up the z-axis all the way out to 2 kilohertz, and you reduce some of the lower frequency, 1500 hertz, 1000 hertz content down within the control, within your limits. But you still have this sharp point just before 2 kilohertz on your bandwidth. So then we add the second mode shape. So again, for the 7 degree of freedom was designed to control that first table mode shape. And then the 8-DOF control was designed to control out as best we can the second one primary mode shape that was within the table frequency band. And you can see that each level of additional control, the 7th and 8th, we've reduced that resonance by some amount, presenting a much more overall control of your table. With that, that's most all we had presented today.
Yeah, very good. Thank you so much, Jordan. So we'll definitely open it up for questions. We have a Q&A module. There's just a little questions box. You should be able to send your questions over. So Jordan and I'll walk through those, and we'll try to answer that the best we can. And we have your contact information, so we can reach out to you afterwards as well. But feel free to send those questions in. I'll also just kind of give you a preview to let you know that we're going to talk more about controllers on future Tech Tuesday with Data Physics. Definitely experts in vibration controllers. So stay tuned for that. And we have a question here that has just come in talking about Okay, with budget constraints in mind, how can we convince the powers that be to do multi-axis test?
Yeah, so I've heard that, time and time again, where multi-axis is a significant cost driver for a lot of programs, especially when, customers have been testing their products for 30, 40 years in the same way, in the same single degree of freedom way. And really, from our perspective, it's, we know it's better. We know it costs more money to do that. And the best way to do that is collect your own field data and prove, well, here's why it's different and why we need to be testing our products a little bit differently. Our sister company, Lansmont, does a really good job at helping show customers, here's the real data that's happening in your world. And, you can get a saver that I showed in the PowerPoint, for relatively cheap to go collect your own field data and see, well, here's what we're actually seeing, and compare that to the test levels that are currently being run in the lab. And so I think that would be my number one recommendation, is to, go collect your own data, even if you're doing typical test standards that are approved, just to see, well, are we seeing something different than what we're actually testing to? And potentially that's going to help improve our product design and provide us with a better, a better product in the future.
Yeah, I think that's great insight and a great recommendation. Okay, got another question here asking what controller was used with the tensor.
The controller that we use with the tensor was the data physics matrix. So I think all of the tensors that we've built so far have utilized that test controller. It was a 12 input channel control for the 12 different shakers.
Yeah, and I guess that's just a good reminder. Again, we will be working on a Tech Tuesday in the near future to really talk more about controllers, to help the customers out there learn more about what data physics brings to the table there. Obviously, you guys are using those, so that's great. With that, I want to thank you all for attending. On behalf of Team Corporation and Data Physics and Lansmont, the NVT team, as well as Vic Myers Associates, we thank you all for your time and joining us today. We'll see you again soon for the next version of Tech Tuesday. Everybody stay safe, and we'll look forward to seeing you out in the field soon. Talk to you later.